My name is, as mentioned, Mats Stellwall. I work at Oracle EMEA as a data scientist. I'm going to spend these next 20 minutes or so to talk a little bit around maybe just Oracle. No, I'm not going to talk about Oracle at all. I'm going to talk a little bit how we can use machine data and we combine that with deep learning and make it a little bit more actionable. Sorry. And there's, to be fair, I mean, there's a lot of devices today. I mean, there was a discussion just previously around how we can use IoT in manufacturing and these type of things. I mean, everything is connected today. Everything is generating a lot of data today. And this is growing quite massively. And I think Cisco has made the predictions that by 2020, there's going to be over 50 billion connected devices. That is a lot. That is many times more than there are humans on this planet. And quite a big part of this is video and photo devices. So, I mean, there's surveillance cameras everywhere. And I mean, I read in the paper just the other day that there's going to be over, I think, 600 or 6,000 surveillance cameras in hospitals in Sweden during the next years. So we are constantly filming and monitoring everything out there. But we also, everyone nowadays, we carrying around devices that is capable of taking pictures and videos of things. Now, still, when we talk about machine data, when we talk about IoT and the use cases, we focus a lot on monitoring. And it's nothing bad in that. So monitoring in the sense of where are my devices? I mean, a simple app is that where is my phone? I can follow my phone through its GPS coordinates, or maybe if I have a hospital, I can keep track of all my assets. So where is the wheelchair currently? Where is the operating table? And these type of things. Or we're monitoring assets based on the health. So how is my machinery performing? What is the vibrations? What is the temperatures currently? And of course, we can use advanced techniques on this, like machine learning, in order to predict when this machine is likely to break next, or what is the most optimal way to go from A to B in order to consume less gas. But it's still based on sensor data. Most of this is sensor data, and I would say kind of a traditional data that is generated from machines. And it is what they say is, a picture is worth 1,000 words, so I thought I was going to illustrate that by not using a picture. But we can do things with it a lot. And today we use kind of, when we're monitoring things, we have a manual monitoring of that. So if we do surveillance of something, there's people sitting and watching what is happening there. And it's kind of hard to catch everything that is happening. Or if we want to do a surveillance on railway tracks or shipyards or whatever, someone needs to sit and assess the data that comes in through this. So if we want to make this a little bit more actionable, if we want to draw conclusions automatically on this data, we can leverage things like deep learning. Now, I don't know how familiar everyone is with deep learning. I realize sometimes that just because I do work with it every day, I take the assumptions that everyone else knows what it is. But I can say most of us have heard about AI, artificial intelligence. I mean, it's kind of the only thing we read about in the paper is how AI is taking away our jobs, or AI is going to make this and that. And in the end, AI is basically really machine learning. It's a very narrow intelligence. And AI and machine learning is nothing new, even if it seems like that when you read the paper. It's been around for a long time. And machine learning has been around for a long time. And even in the late 50s, the first neural network was created. It was a very simple neural network. It wasn't as advanced as they can be today. But the first one was created, and the first application based on neural networks was also developed, which was around eliminating echoes on phone lines. And this is something that is still in usage today. Now, if we move fast forward from the late 50s to the early 2010s, we have the rise of deep learning. And deep learning is basically a way for us to run really, really huge neural networks. And the challenge with these deep learning networks is that they consume data. They consume a lot of data in order to be this accurate and this good. And they consume a lot of compute. So one thing that helps us with this is the rise of the cloud, where we can get almost unlimited compute resources. But also another thing in this is image and video data or sound data that is by its nature is really, really big data. If you think of it, if you take a picture, not a big picture, let's say 800 by 600 pixels, and it's in color, so you have 3 channels. So you have 800 by 600 by 3. That is the number of data points for just one picture. If you have hundreds and thousands of these, this gets really, really big really quickly. But that is why deep learning is so good for these type of problems. So when it comes to video and images, there's a number of use cases or a number of applications we do with this. We do mainly what we call image recognition and something we call object detection. Now, image recognition is basically what is it in my image? What is the primary object that is dominant in this? And we put the label on that and say, well, this is a cat. It is a simpler thing to do, but it's still powerful. Object detection, on the other hand, is more about the number of objects we have in the pictures. So we have a cat and a dog, and where they are in the picture. And this makes things a little bit interesting. So we can say that there's a dog and a cat in this picture, and we can also tell which coordinates they are at. So this is the cat, and this is the dog. Where we do image recognition, we say there's a cat in the picture somewhere. But where it is, who knows? But we can see it somewhere. So this enables us to do a lot of things. So if we think about it, if all of us always carrying around the phone, why don't we have services where we can enable to take pictures of something? So for example, I have a citizen chatbot, which is coincidentally named Proxima City, which is something that we have outside. But I could communicate with that and say, well, I want to report an accident. And the answer would be, but please upload a picture. So we upload the picture, and we can see these Lego figures. They are not that good at driving, so we have an accident here. We feed that picture into the system we have, and we start identifying things. And my apologies for, well, it looks better there. We can see what is there. So we can see that there's 2 vehicles, and there's 2 Lego figures in that. And we can take that and send back as a feedback. So we say, well, I can see that there's 2 vehicles, 2 figures in this. Please confirm. And by confirming, we can also enable what we call a feedback loop in this to say, verify that the learnings that we do is correct. And if they are not, we can start adjusting. And if they confirm and say, well, yeah, that's true, well, we can then trigger something else in the back end to say, well, let's then send the service request to the back end system so we can dispatch resources to this. But it is something that gives me a good, something good that I can do. And I mean, we don't need to just report that someone has an accident. We can do it for things like, well, there's a broken street light here. Why don't I take a picture of that and send it in, and it automatically be assessed, and they create a service order and send out someone to fix it. Now, other things we can do with this, and if we have a video camera on our platform, why don't we count the number of people there? So currently at Lego City, there's 8 people waiting for the train on the platform. And we can use that knowledge in a way to say, well, do we need to add more trains? Do we have too many people on the platform? Are people based in the wrong area of the platform? Maybe we should do an announcement to say, you know what, the train is quite long. You don't have to stand in the middle, all of you. We can move around. But we can also use it for other things. So how many people are currently in my store? Most stores has cameras that monitoring people entering and exiting. Why should we set up sensors to triggers when someone passed by when we can count them by camera? And we can use that knowledge to see, well, now there's a lot of people, we need to do something around the checkout lines. We need to add more people. Or how many people are there really at my construction site? According to the passage system, there should be 50 people, but I can count 55. Or at at the rails for the trains, there might be people moving around there unnecessarily. But of course, we don't need to count just people, we can count other things. So how many cars are passing by now? How many containers is there that I need to be moving around? And so on and so forth. So we can do a lot of things with this. And of course, when I was mentioning construction site, why not identify people that is not having the right security equipment? So we can mark that in a good way to say, well, there's two guys there, and I'm sorry for this, that it might be so, but they don't have helmets. We need to have helmets. Otherwise, something can happen, especially for the poor guy there that has a crane above him. But we can use these type of things to automate and take action, because the action would be to send a notice to someone to go out there and say, well, you need to put the helmet on. But we don't need to constant monitoring this. So how is this done? I mean, is it just to send some pictures to Oracle and we will fix this? No, not really. Transfer learning, it's the golden nugget of deep learning. I would say that transfer learning is one of the single greatest things about deep learning. And basically because, as I mentioned, when we do deep learning, we need a lot of data. And when I say a lot of data, I really mean a lot of data. So if I'm going to train that model from scratch, to say from ground zero and up, I need to have thousands and thousands of pictures of each and every object I want to identify. And I don't just need to have pictures, I also need to label all these pictures. I need to go into every picture. I need to mark with boxes or something similar to say, here's a figure, here's a car, here's a dog, here's whatever I want to identify. I need to do that for every picture I have and store that. Then I need to start training these networks. I need to design the network, I need to train it, which means I need a lot of compute. Because if I don't have a lot of compute and GPUs, it will take forever. It will take days, weeks, months. So now compute is kind of easy to get access to today. That is not a big problem. It's just a matter of cost. I can spin up a lot of GPUs quickly. But the data is kind of the challenge today, because not everyone is like Google and those guys that has access to a huge amount of picture data. But the good thing with transfer learning is that I can leverage what other has done. So in this case, there's people for research and so on that has trained models to identify different types of objects. They have not trained to identify Lego objects that I particularly was training in this case, but they have been trained to identify people, cars, and these type of things. And I can leverage that in a good way to say, well, you know what? Some of the features are similar between a Lego figure and a man in colors and how we do things. So I don't have to get thousands and thousands of pictures. I can get just a couple of hundred of pictures. I don't need to train for months. I can train for hours, and I can train with less compute capacity. So that is why transfer learning is a key to do this quickly. So when I develop this, what do I need? Well, I need an instance, a compute instance. And of course, if I have a GPU, that is fine, because that makes life easier and faster, but I don't need to have a big one. I need to have a deep learning framework that I can use for doing this training. And in this case, I'm using TensorFlow, and I'm using Object Detection API, which is a part that TensorFlow has released. And I'm going to go into why I'm using that, but that is a really cool thing. And I need some data. But not that much. But I need example data of whatever I want to identify. So if I would identify real people, I would still need to maybe do some retraining of these models, because I want to get pictures that describe the environment where I want to catch them at. So if I have a train station, I want to take pictures that is within my train station so I can make sure that I can identify them, but I don't need that much. So why TensorFlow object detection API? Basically because I'm lazy. I'm really, really lazy. And this is what I need to do when I'm using this one. I don't need to code. It works with pipelines. So what I need to do is I need to have a configure file for my pipeline where I said, this is the model design I'm going to use. This is how I'm going to train this model. This is the data I'm going to use for training. This is how I evaluate it, and this is how I'm going to read the data for evaluation. It's very easy. It's very simple. I can focus on more interesting things like understanding the behavior of the model. Do I need more data? Do I need to do argumentation? And these type of things. But I don't need to code. And for me, that is kind of a great thing. And even the better thing is, for this objection detection API, there's already pre-trained models that I can download and reuse and start using. There's already ready done configuration files. So I don't even have to fill in this. I just have to point to my new data and do it. So this is a good thing. And maybe it's not a good thing at the Oracle employee talks so good about the Google product, but that's life. So, production. Nothing is valuable if we don't put it in production. If we don't put it in production, it's useless. So, easiest way to consume this is to do it as a service. So, having it run on a compute instance or a container instance, having an REST API on this, and in this particular case, using the simple possible solution, using Flask, which is a Python framework for doing REST servers for it. I don't have to have GPU instances. I can use CPU instances. GPUs give me a great flexibility for training. I can get away with cheaper CPUs when I'm doing the interference. And of course, there's a lot of other things behind this in the sense of, well, the accuracy and the speed of the model. I need to decide on that as well, because the bigger the model, the better the model, probably the bigger it is, and it takes more resources. The smaller the model, well, it's less accurate, but maybe it's accurate enough. Because we don't need to be, depending on the application we do, we don't need to be 100% sure. We just need to be enough sure to be able to do whatever we want to do. But having this as a REST interface, I can use whatever I want to use to call it. So I can send in my picture, I can get my result back, and I can connect it to whatever I want to connect it with. To end up, I'm going to end up with a shameless plug. We are situation in the booth outside. You might have seen it or not seen it, but we have implemented part of this in what we call the Proxima City, which is a Lego city built with Lego using Oracle platform for doing these type of things. There's going to be more in-depth presentations of this. I think it's 3:30, where we're going to show more in detail how it's done and also go into more details of how it works. And this is everything I want to say, and I hope you have enjoyed it. I surely have. Thank you.